about a quick application of functions, which has to do with cell phone usage. There's actually ways to write a functional representation of something and of different things. And so one example is with cell phones. The example given here talks about a roaming charge for a cell phone. Let's just say it's $2 to create a connection and 25 cents per minute. If n represents the number of minutes of a call and c represents the charge for n minutes, write a function that represents c and evaluate it in a 10-minute call. This is real life application, right? So I grew up in Nigeria. Whenever I have to fly back to Nigeria, I have to make a decision. Am I going to buy a new cell phone in Nigeria, or am I going to collect roaming charges from my phone in America? And so what you do is that some networks will tell you it's $10 per day if you want to sign up for international calling. And then they might charge you like 10 cents per minute. So you're paying for the service to use it on a particular day. So let's say I'm traveling for 7 days. And during those days, I want to use my phone for 10 minutes per day to call and check on you guys and see how's it going. So basically, I can write a function for my situation. Your book gave you an example, and they wrote a function for their situation. But basically, it is $10 per day plus 10 cents, right, per minute. So if somebody says, this is like a function representation of my phone, and let's call it, if we're looking at it, so we know that we're going to use 10 minutes, right? And this is a known fact. So I'm actually going to clean this part here, and I'm just going to say +1. The reason why I put +1 is because we know we're going to use it for 10 minutes a day. This part is saying the function is P of D is equal to $10 per day. So if I'm going to be there for 7 days, how much should I budget? It should be $10 times 7 days plus $1 per day, right? So that's technically going to be 7 as well. So I apologize, I should have put my D there as well. We can add them together if we want, but I'm just trying to show us how we're plugging in the values. So you're going to put $10 per day for 7 days, so that's $70. Plus, we're going to have each day spending $1, so that's going to be $7 total. So on my trip, I should budget $77 in order to make sure I cover my phone bill and not get a late charge, etc. Okay? So that's an example of how we use functions. We can write a function to describe phone usage when you travel overseas. Now, your book gave you the example of C of M is equal to 1 plus 0.25 M, which is simply saying that you need to pay $1 to connect to this service. That's what this one is. And then you're going to pay 25 cents per minute for making calls. So depending on how many minutes you use, you just add $1. That's how much you owe the phone company. Isn't that pretty practical? I think it is. This is a practical example of functions. Let's talk about interval notations, and then we'll wrap up with linear functions and slope. With interval notation, it is important to know that the things you learned in middle school and elementary school, such as less than and greater than, apply in this context as well. So less than can be represented by that sign, right? So we know that's less than, that's greater than, right? That's less than or equal to, that's greater than or equal to. Okay? So how is this on a practical level? We know that if somebody says x is less than 5, we'll write it like that. But somebody could ask you to write that in a different notation. There's notations where you're using a number line. Like in this case, if they said x is less than 5, you go to 5, you draw an open circle and go in that direction. That's the notation of x is less than 5 using circles. It's an open circle because it said x is less than 5. It doesn't say less than or equal to. And then notice that this looks like this. Notice the connection there between this and that. The arrow is pointing that way. So x is less than 5. Now, there is another way of noting that x is less than 5, and that's by using a parentheses. So if somebody says x is less than 5, that means that 5 is the greatest number in this situation. Well, it's not the greatest, but it's the number on the other side of this parentheses, and everything below 5 is part of the solution. So in math, we just write it like this. We say negative infinity to 5, because if you're going this way on a number line, you're going to negative infinity. And then if you're going that way, you're going to infinity. That's how we can represent x. So x is less than 5, x is greater than 5 would be going in the opposite direction. So we use parentheses when it's just x is less than 5. If we said x is less than or equal to 5, that will change quickly. This will become a number line with a shaded, like a closed circle going in that direction. And this will become a bracket with the negative infinity part. Let's just talk about the rules with infinity and negative infinity. There's no limits for the infinity part. So you can't put a hard bracket. The hard brackets would be including that number or that value. So we can't do that with infinity or negative infinity. So if somebody says, what about x is greater than or equal to 5? Then we start at 5 and we go to infinity and we use a parentheses there. We never use a hard bracket with parentheses, with infinity or negative infinity. Okay, so that's a little bit of notation here. Less than, greater than, less than or equal to, greater than or equal to. Negative infinity and infinity are used for these notations when you're using brackets. These are called brackets. We also use parentheses depending on the situation, right? There's parentheses that can be used. So then we have parentheses. We have open circles and we have closed circles. These are all important for interval notation. Okay, so that is the interval notation part. I'm going to wrap up with linear functions and slope, and then we'll be done. With linear functions and slope, the first thing to remember again is your slope-intercept form, which is y is equal to mx plus b. Your point-slope form, which is y minus y1 is equal to m into x minus x1. Your parallel and perpendicular lines are discussed. All of this are done in detail in Tyler Wallace 2.1 to 2.5. So let's look at a few things here that we need to know, and then we'll begin to wrap up our session there. The one thing I do want you to know too with functions is we use the word domain and range with these functions. And when you're dealing with linear functions, right, which is the specific here, if I draw a sketch of a linear function here, this is like y is equal to x. This is y is equal to x plus 2. So notice that if you move the graph up 2 times, this is just a quick preview of what's going to come later. This is called a graph transformation. You can move it up 2 spots, and that will allow you to just sketch a new graph. The domain of both of these functions and any linear function is from negative infinity to infinity. That's the domain. All values are okay. And that is the same with the range. All values are okay. Because there's no value for a linear function that you give me that will be undefined if it's a linear function. That's just the nature of linear functions. Okay? So that's what we do there. We're going to end our section here with parallel and perpendicular lines. If 2 lines like these two have the same slope, we call them parallel lines. So parallel lines, the slope of the first is equal to the slope of the second. Okay? So that's parallel lines. Now, what is the slope of a line in the slope-intercept form? If somebody gives you a problem like this, and they give you a problem like this, the slope 1 is 2. The slope 2 is also 2, right? So I'm calling this M1 and M2. M1 representing the first equation, M2 representing the second equation. The y-intercepts are different, but the slopes are the same. So parallel lines have the same slope. So slopes are the same. If the slope is the same for 2 lines, they're parallel. If the slopes, when you multiply them together, gives you -1, those 2 lines are perpendicular. That means that for 2 lines to be perpendicular, the slope of the first one and the second one have a relationship where it's the opposite reciprocal of the second slope. So the slope of the first line equals the negative reciprocal of the second line. If that's the case, those 2 lines are perpendicular. In math, there's a lot of if-then statements, and you have to realize in life we use that all the time. If this, then that. If the traffic light turns to red, then I stop. if this, then that. That type of thinking is very mathematical, and ultimately, the more you learn math, the more you learn logic, the better you'll be at doing so many other things in life. I hope this was helpful. We'll see you in the next video.